Welcome, everyone. It is our great pleasure to welcome you to another session of Data Science and Statistics webinar. And today we have the pleasure of welcoming Mário Figueiredo. Mário is a distinguished professor at the Instituto Superior Técnico of the University of Lisbon within the Department of Electrical and Computer Engineering and is holder of the Fedzai Chair in Machine Learning. He's also group leader at the Instituto de Telecomunicações. Mário is fellow of different institutions like IEEE, the International Association for Pattern Recognition, European Association for Signal Processing, or European Laboratory for Learning and Intelligent Systems, among others. He has received several awards. He is member of the Portugal Academy of Engineering and corresponding member of the Lisbon Academy of Science. And between 2014 and 2018, he was included in the annual list of highly cited researchers. Mário research interests include statistical machine learning, signal processing, and optimization. And today he will share with us his recent work on how to deal with strongly correlated variables in supervised learning. Mário, thank you very much for accepting our invitation. The floor is yours.
Thank you very much. So thank you very much for the invitation to take part in this interesting webinar series. I actually attended a couple. Actually, I saw the video. I didn't attend in real time. So what I'll be talking about today is not very recent work, but it has some very recent ramifications, which I will talk about in the end. But I'll start with very slowly, so probably with things that you are very familiar with. But then I'll go on to talk about what contributions we've done around this topic and modern applications, namely for deep learning and other sort of more modern machine learning topics. So this is a brief outline of the talk. So I'll begin by just to set the stage, talk a little bit about feature selection, especially in the case of for supervised learning, namely for regression and classification. Then I'll talk a little bit about one of the important problems that people are faced with when dealing with high-dimensional problems, which is the presence of highly correlated variables, which makes all these most of classical algorithms struggle to handle these situations. I'll talk a little bit about two classical approaches. Well, one classical approach and one new one, which is the one we introduced a few years ago, called OWL. Then I'll talk a little bit about theoretical properties of these methods to deal with these correlated variables. I'll talk very briefly about how the corresponding optimization problems can be attacked, because we'll have to deal with with new type of optimization problem to solve these regression classification problems. And then I'll talk a little bit in the end, if there's time, on more recent extensions and applications of these ideas. Is the sound okay? Can you hear me well?
Yes, we hear you perfectly.
Thanks. Okay, so as you all very well know, we'll be talking about, well, we know what linear regression is. This is a picture from one of my introductory classes about linear regression. So of course, the goal here in linear regression is to build a little machine that learns how to take in a vector of predictors and produce a response, an estimate of some response, which is a linear combination of those predictors. And this is, well, very nice because it's interpretable. We can look at these coefficients and know what they mean. They mean the rate of change in response per unit change of that particular predictor. And so people like linear regression because it has this property of interpretability, and it's because it's simple to use when it makes sense to apply. So to do linear regression, people typically use a sum learning algorithm, which takes in a collection of examples, say n examples, of pairs where each example contains a predictor variable, predictor vector, and the desired response for that particular example. And the goal of the learning algorithm is to produce an estimate of this parameter beta, which contains the weights of each of these regressors. There is, so although throughout the talk I will essentially keep on using this notation for linear regression, there's no loss of generality, because we can think of these x1, these vectors themselves as being features which correspond to nonlinear functions of some other variables. So just to keep notation simple, I'll focus on linear regression and linear classification. Okay, so linear regression is more formally a very old problem. It goes back at least to the late 19th century, to Pearson and Galton. So just to introduce notation, so we're given n vectors of p dimensions, which are typically called features or variables. So we think of them as vectors in RP, and we have n of them. And we also have the corresponding responses, which in the simpler case of linear regression is just a real variable. And the classical model for this is that each response is some offset plus a linear combination of the components of each of the examples plus some noise. So this equal here is the typo. And of course, these betas are the regression coefficients. Without loss of generality, I will assume that there is no intercept, no bias, although this could be easily introduced. And the noise is often assumed Gaussian IID, but that's not necessarily so in general, but that's the common thing that's done. And in vector notation, we can write this compactly as the vector response is the so-called design matrix multiplied by the vector of regression coefficients plus a vector of noises. So as most of you, I guess probably all of you know very well, this is called the design matrix, and it's n by p, where n is the number of samples and p is the dimension of the regression coefficients. And of course, the goal in linear regression is to estimate beta from y, from the vector responses, and from the design matrix of the examples. Okay, this can be easily generalized to other nonlinear cases, such as logistic regression or some other generalized linear model. And this is another classical example where your observations now are binary outcomes, which are samples from some binary variables, which are conditioned on each example feature vector. And the way we produce probabilities, probability that each of these y's equals 1 is some so-called logistic transformation of some linear function of the coefficients of the predictor variables or features, whatever you want to call them. So this is called logistic regression. Again, the goal is the same. We have n examples, and the goal is to estimate beta from those examples. Okay, so in general, we may be dealing with either linear regression or logistic regression, or on any other. This could be Poisson regression, any other generalized linear model. But I'll keep these two as examples along the way. And one of the tasks with which people that solve these kinds of problems are always have to deal with is the selection of which of these variables are relevant. So is it true that all these components of these vectors are all relevant? Should some of the betas, which is the same as saying, should some of these variables be ignored, corresponding to, should some of these components of beta be 0? Are they all relevant or not? Are they redundant? So are there groups of features that essentially have the same information, so we should maybe discard them or not? Or what should we do if they're redundant features? And so feature selection is a very old problem in statistics and machine learning, and essentially it has been addressed with several different types of methods. So there's a paper like some 30 years ago which classified the feature selection methods in essentially 3 classes. So which are the filters. So the filters, in filter methods, the goal is to try to assess the relevance of features without taking into account what they're going to be used next, so ignoring what the learning algorithm is going to be used next. And these filters could be supervised if you know the responses. It can be unsupervised if you use only the features. So typical supervised filters would be something like assessing the correlation or the dependency between each feature and the response. And if this dependency is very small, then you probably would think that this feature is not very relevant and you would discard it. Wrappers are methods that, as the name implies, are wrapped around some learning algorithm. So typically what you do is you have some method to go over different subsets of features, and then you use those features on a learning algorithm that is then evaluated in terms of performance to assess how good that feature subset is. And then you need to build on top of this, you need to build some search procedure to go over all possible collections of features, or maybe not all, but some way of searching through these combinatorial space of feature selection choices. And then finally, this is called embedded methods, which is the ones which we will be looking at, where the learning algorithm itself, in its objective function, contains something that takes care of selecting features, that is, of discarding features that are not relevant. So taking into account these facts. Okay. So how do these embedded methods typically work? So for that, we'll need to go back to this classical way of addressing, say, linear regression, which is typically by formulating it as an optimization problem, where you're trading off accuracy, so fitness to the data. So you have a loss function that essentially measures how well, for a given choice of your parameters beta, how well your predictor is doing at predicting those labels that are present in the training set. So this is typically called the cost loss function or a cost function. And it measures how well the data is being fitted by your model, by your estimate of the parameters. And then there's a regularizer, typically, which somehow expresses desirability, like should beta have a small norm, or should it be sparse, or should it have some other characteristic that you think is important. And so typically this is formulated as an optimization problem, where you solve this optimization problem that includes minimizing the sum of the loss with the regularizer. And this goes by many different names, like penalized maximum likelihood. It can also be seen from a Bayesian perspective as a maximum a posteriori estimate. If L is a negative log likelihood, and so in that case the regularizer is minus the log of a prior. And so the same formulation can have different semantics depending on your taste on these matters. And one of the reasons that why these approaches are very used and studied is that often you have a nice characterization of what your solution is, because you can characterize it as a minimizer of some function. And that typically, or maybe hopefully, it will open the door to some analysis that you can characterize the solutions to this problem. So the classical example of this is, of course, linear regression, where the loss function is simply the sum of the squares of the differences between the responses and the predictors and the predictions. Predictions are obtained by multiplying the design matrix by the regression coefficients. And the regularizer is something that we may choose. So the old classic that everybody studies in introductory statistics is ridge regression, which goes back, well, I like to cite Wiener, because he did something very similar, although he didn't call it ridge regression, but the Wiener filter is essentially a ridge regression. But in the statistics literature, this is attributed to Hurl and Kennard in the 70s, in 1970 actually. And when you use the regularizer, this just square Euclidean norm of beta, and you combine these with this squared loss, the problem has a closed form solution, which is well known. It's just amounts to inverting that matrix there. And many years later, people, when faced with the problem of trying to select features, they addressed this problem by using something very similar, but where there is apparently very minor difference of replacing the squared Euclidean norm, squared 2 norm by the 1 norm, led to sparsity. So the 1 norm, as I'm sure you know, is the sum of the absolute values of beta. And so the fact that you're regularizing with the sum of absolute values introduces a qualitative difference in the solution to this problem. Okay, so there's ways to do it formally, but I'm not going to do it. So, but essentially, if you look at these circles as level curves of these squared error loss, and at these red sets here as level curves of the regularizer, if you have the squared Euclidean norm, so level curves of squared Euclidean norm are circles. So when you're minimizing the sum of these two, you can reformulate these as minimizing one with some upper bound on the other. And so the solution will be in general position anywhere on the plane. But when this is an L1 norm, what happens is that the level curves now are squares, rotated 45 degrees. And so for many different positions of the level curves of this function, okay, the solution, that is when the first time that the level curves of these meet the some level curve of these, may happen on an axis, okay? And this is true for non-zero measure set of positions where you can put these. So whereas, of course, on this left side, this could also happen here, but it's only for one specific choice of the position of these circles. Here it happens for a wide range of choices, and so there is sparsity coming out of this choice. So this is very famous. It's called the LASSO, least absolute shrinkage and selection operator. It was introduced in statistics literature by Tibshirani in the mid-90s, although actually this had been used in signal processing at least 20 years before, in different applications, so in geophysical signal processing and in other areas of signal processing, and also in the neurosciences. Okay, so in logistic regression, the story is the same. I'm not going to go into details of why the logistic loss looks like this. It's a classic in statistics and machine learning. So the idea is that you can also use ridge regularization for logistic regression just by adding square Euclidean norm with some weight. And you can also use sparse logistic regression by using, again, the L1 norm. And it can be, it has the same effect. So by using L1 norm, you encourage solutions to have some zeros, so that is to be sparse. There are, of course, many other generalized linear models can be used, not only linear regression and logistic regression, but I'll stick to those two. Okay, so correlated variables, okay? So suppose that your goal is not only to be good at predicting new values, so that doing good prediction, but you have more scientific goal, which is to identify all the relevant features, okay? And why would you want to do this? For example, if the variables have some meaning, okay? Suppose you're learning a predictor to some disease from, say, gene expression data. So you have your vectors of predictors are the level of expressions of a collection of genes, and you want to predict some disease. Of course, it's good to be accurate at predicting the disease, but it's also interesting and valuable from a scientific point of view to identify which predictors, which genes are predictive, because that may have scientific meaning. And so you don't want to just throw away all the variables that are not relevant because maybe they are redundant, because there are others that do the same. You want to identify them all. So this is just a picture that doesn't mean much. It just means that, just to illustrate this idea that in some situation you have thousands of features and maybe only tens to hundreds of samples. And so the probability that you have many features that are very, very highly correlated and that in principle you wouldn't need them, maybe that's not a good idea, because the fact that they are predictive has information that may be valuable. So this is the setting in which I'm interested. So this is just a summary of the sentence of what I just said. So, however, if you try to use the classical techniques, such as LASSO, so penalize with L1 loss, these may not work very well. And let me explain visually why this is so. If you have in this objective function of the squared loss, if you have highly correlated features, imagine if you have only two features, suppose that beta has only two components. And in the extreme case where the two features were exactly, one was a copy of the other, instead of ellipses, you would have like just a straight line, because the function would be flat in one direction. And in situations where that happens approximately, because you have columns of X which are very, very highly correlated, in that case you will have the level curves of this term of the loss function will be extremely narrow and very, like, these very long and sharp values. And when you combine these with the L1 regularizer, the solution will be extremely unstable. So where these green squares first touch some level of the level curve, it depends on minute changes in the data. So say, for example, on fluctuations of the noise. And so it has been shown, and in the famous book by Peter Bullman, that in this situation, these linear regression or any other type of generalized linear regression with very highly correlated features becomes extremely unstable. And actually ends up selecting an arbitrary subset of features. And let me illustrate some of the approaches that have been used before. So if you know which variables are correlated, okay, then this may help, okay. And you could somehow try to learn which variables are correlated and try to inject this information into the system. Okay, so one of them is, suppose that you know, or you estimate the covariance of your training data, of the features in your training data. Let's call it sigma, okay. Then you can take this covariance information. You can look for the correlated features. You can use this correlation as some distance, as some similarity measure, and you can cluster the features. Okay, this is something called cluster lasso. And then once you cluster, you can either use group lasso by grouping those features in one group, or you can just take a group and select one representative for that group. And so by doing that, you're sort of not doing what we wanted to do, which is keep all the variables that are relevant and that are predictive, not just use a subset of them. Another way of doing it, I'm not going to explain this in detail. It's just you can take these covariance and you try to encourage by looking at the magnitude and the sign of the covariance. You can try to add to the objective function that you're trying to solve a term that encourages the coefficients of features that are highly correlated to be close to each other. To try to group the coefficients in agreement with the correlation of the variables. So this has been proposed a couple of years ago. And there are several variants of this approach going back to say 10, 12 years ago, and all the way to more recent work in 2000. Actually, there's follow-up work of these in 2019. One of the key aspects of this approach is that it is expensive. If you have, because this scales quadratically with the number of features. So to compute correlation between all pairs of features, if you have p features, of course, you need the cost of doing this scales quadratically with the number of features, and this is undesirable in situations where you have a lot of features. Another approach to break this symmetry problem between highly correlated features and the L1 norm is something called elastic net, which I'm also sure some of you will know. And the idea here is to try to include groups of correlated variables. I will explain graphically what this is doing, okay? So in elastic nets, I will draw the picture. So suppose that the level curves of our loss function of the part of quadratic squared L2 norm, so the loss term of the objective function, are these ellipses here, so this would be the least square solution, okay? And in this situation where the variables are correlated, these ellipses are kind of narrow and tilted at around 45 degrees, assuming that the columns are normalized, okay? And if you use the L1 norm, so the L1 norm is this dashed blue line inside, okay? Which has this problem that it's almost parallel to the sides of these ellipses, and so the solution will become unstable. So what the elastic net does is add to the L1 norm, also an L2 norm, so the squared Euclidean norm. And so this green line is sort of a slightly inflated version of the L1 ball. And so it kind of breaks this symmetry around this line. And OSCAR, which stands for orthogonal shrinkage and, I forgot what it stands for. Oh, it's here. Orthogonal shrinkage and clustering algorithm for regression. It's a nice name, which was proposed in 2007. What it does is add this term. So this term is, it adds to the L1 norm. So the L1 norm is the sum of all the absolute values of the betas. And this other term is an interesting term, which is, it's the maximum across all pairs of coefficients of the maximum of the absolute values of each of these pairs. If you look only at two coefficients, so in this case, I'm looking only at two because I'm on the plane, the level curve of this function is orthogonal. Is this octagon here. And so what this does, it has some preference for solutions, because solutions in this case are always places where there's an intersection between some level curve of the objective function, of the loss function with the regularizer. because it has these vertices here, because it's a polygon, it has some preference for solutions where both coefficients are equal. So what this does is encourage beta I and beta j to be equal to each other. Or another way to see it is that if one of these betas is already being used, the other one pays nothing for having a value that goes all the way up to the value of the other, because only the maximum of the two is paying some price for being in the loss function. Okay, please interrupt me anytime, okay, if you have questions or if I'm saying something that is not clear. Okay, let me just illustrate this with a very simple linear regression problem. Suppose you have this design matrix, so you have 10 samples in 30 dimensions. So I'm doing linear regression. And this is a very weird matrix because the regressors are perfectly correlated in groups of 3. Okay, so first 3 columns are equal, second 3 columns are equal. Of course, this is a toy problem. And suppose that your true predictor, so the true data was produced by this beta star, which has this shape. So we have this, you're using group number 3, 5, and 8. And if you use lasso on this problem, you get something like this, but you could get something else. Okay, you don't know exactly what you get. Any solution which is in the convex hull of these 3 values will be okay. Okay, they all give you the same. Whereas Oscar encourages the 3 coefficients to be equal because they correspond to columns that are highly correlated. And so Oscar recovers the true one. So I'm not saying this is good, because if this was the true one, the solution would also be these. But the question is, under this matrix, these and these are absolutely indistinguishable because they would produce exactly the same prediction. Well, not apart from the fact that the value is not correct. So these are results from Bondel and Reich in 2007. So they tried these on lots of different data, and they found out that Oscar was actually very good. It was better than Elastic Net in terms of prediction error, in terms of degrees of freedom. So it achieves lower prediction error with lower degrees of freedom, and it's competitive with Elastic Net, and it's better than Lasso. It's better than Reed in terms of MSE. And the advantage it has also is that it explicitly groups the variables. So it says that, let me give you an example. So this is a very simple example, only with 15 predictors. It has coefficients that are exactly equal, even up to sign changes. So what this is saying is that these 5 variables here, the 5 variables that correspond to these 5 coefficients, are perfectly correlated. So they're being treated as if they were the same predictor, and they are inversely correlated also perfectly with the other variable here, pH. And so the linear regression solution will treat these variables as if they were only one variable, but it doesn't throw them away. It keeps them all here, but it treats them as if they were a group, if they were a single variable. Okay, so this is our starting point. This was our starting point. So now I have the stage already set. And so we have this regularizer Oscar, which is this octagonal regularizer in 2 dimensions. In higher dimension, it has stranger form. And the first observation is that this regularizer can be written in a more interesting way, in this way. Okay, so instead of having this one norm plus this sum of the maxes of the pairs, this can be written as a linear combination of the components of beta, sorted after you sort them in non-increasing order. Okay, with coefficients that are given, but they're linearly decreasing. Okay, this is easy to understand why this is so. So if you think of all these pairs of betas, the maximum of all the betas across all the p beta, the maximum of them will appear p times. Every time it's compared with all the others, it will appear all the times. Every time it's whole him that's bigger than the others. The second largest will appear p minus 1 times, and so on and so forth. Actually, the largest one will be p minus 1, the second largest p minus 2, and so on. And so this is why we have this linearly decreasing sequence of coefficients, multiplying the coefficients, the norms of the coefficients, after sorted in decreasing order. Okay, so what we did in 2014 actually, and then continued on studying this regularizer, was generalize it this thing to not necessarily linearly decreasing sequence, but for any decreasing sequence. So we call this the order weighted L1 because it's a norm. I'll show you in a second. It's a norm, which is defined as this. So for any given parameter beta, which is the argument, this W is parameterized this function. And the way you compute it is you sort the entries of the argument in decreasing order of magnitude, and then you compute this inner product between the two. Okay, it can be written in closed form, in compact form, as the inner product between the coefficients W and the sorted vector beta, which is with a down arrow, which denotes sorted in decreasing order of magnitude. Okay, so this is the owl, and that's why we have the picture of the owl next to the definition. Okay, so it's actually a norm. It's easy to show as long as the first coefficient is not 0. It's actually strictly positive. It is closely related to the L1 norm and to the L infinity norm, as I'll show you. So it's upper bounded and lower bounded by this sandwich of inequalities by the beta 1 norm, by the 1 norm, where in the upper bound you have the largest coefficient, and on the lower side you have the average of the coefficients. And it's related to the L infinity norm, that is the maximum absolute value of all the entries, but that's not very important. Okay, so one of the first experiments with OWL on large-scale machine learning problems was on a PhD thesis in CMU in some 6 years ago, where this is essentially, if you can think of it as a very large dimensional logistic regression problem, very large. So the number of parameters is something like of the order of 700,000. And what this shows is that if you use elastic nets, so regularized with L1 plus L2, you do achieve some regularization. So because some sparsity, so you go down from around 1 million parameters to 55,000 non-zero parameters. But if you use OWL, you actually go down to 922 unique values. So there's 677 non-zero coefficients, but only 922 different values, which means that these 600,000 coefficients share 922 values, different values. And so that's what in the neural network literature is known as parameter sharing or weight sharing, which means that there are only actually an order of a few hundreds of different values that are being shared by the hundreds of thousands of different parameters of the system. Okay, so it suggests that OWL is able to learn the weight sharing that is relevant for some problem. Okay, I will skip this. So there's more applications. So this is 2018. I will probably skip this in the interest of time. It's an example. Just I will skip it. Okay. So the interesting part is, what can we say about the solutions of these that are, say, for linear regression? What happens? What can you say about the solutions that you obtain when you use this OWL norm as a regularizer? Okay, to study these, we actually resorted to an interesting area of mathematics, which doesn't seem to be related to this, but it turned out to have the right tools, which is the theory of majorization and of sure convexity. Just very briefly, I'm sure a lot of you know this. So majorization is a relationship between vectors in some dimension. So you have two vectors, beta and gamma. We say that gamma majorizes beta, which we write like this. Actually, it's the other way around. This is incorrectly denoted. If the following conditions hold. So if the sum of the coefficient, if some of the components are the same for the two vectors, and all the partial sums of the betas, after being sorted in non-decreasing order, are dominated by the corresponding sums of the others. So let me just, intuition is simple. So a more uniform vector is always majorized by less uniform vectors. Okay, so 4, 0, 0, 0 majorizes 3, 1, 0, 0, and so on and so forth. And so the more uniform the vector is, the further to the left it is in this order of majorization order. So if majorization happens in both directions, this means that the one vector is a permutation of the other. So this goes back, so these ideas of majorization go back to the study of economic inequality in the beginning of the 20th century, as it kind of obvious. closely connected to majorization is the notion of Schur convexity, which was introduced by Schur in the picture there. And a function is said to be Schur convex if the following happens. If you have a vector that's majorized by another vector, then this function is less or equal than for beta than it is for gamma, than for the vector that majorizes the other one. And so, which means that this function is Schur convex if it achieves lower values for when its argument vector is more uniformly, is closer to being a uniform distribution of values. Okay. And we also say that a function is strictly Schur convex if whenever beta is majorized by gamma, but not the other way around, so it means that beta is not a permutation of gamma, then this inequality here is strict. Okay, so examples, we all know lots of examples of Schur convex functions that favor in the sense that they are smaller when they have more uniform vectors. So any function that is symmetric, that means it's invariant under argument permutation, and is convex, is also Schur convex. So for example, the L1 norm, so the sum of the absolute values is Schur convex, but it's not strictly Schur convex. The L2 norm and say the Shannon negative entropy are strictly Schur convex. And finally, there's this almost finally this definition of P-Gould-Dalton transfer, which was also created in the study of inequality. Which suppose you have a vector of say wealth values for some population of P people with some wealth values beta 1, beta 2 up to beta P, and the P-Gould-Dalton transfer is the following: you take the wealth of the ith person and which is larger than that of the jth person, and you subtract some quantity epsilon from the wealth of beta I and you add it to beta j, but you don't subtract too much in the sense that you will not reverse their positions in the order. And so you create a new sequence that a new sequence of values where you reduced the difference between two of the components of the vector. Okay, this is also called for obvious reasons a Robin Hood transfer, because you take a little bit from the rich to give to the poor. And so the P-Gould-Dalton transfer also has a very important role in this study of majorization and Schur convex functions. So to study our norm, we created this notion of which we call strong Schur convexity. Essentially, just says that if some sequence gamma resulted from a Robin Hood or P-Gould-Dalton transfer of size epsilon applied to beta, then the reduction in the value of this Schur convex function is lower bounded by the size of the transfer times the modulus of strong Schur convexity. Okay.
Mario, sorry.
Yes, go ahead.
You require this for all pairs, right?
Yes,
IJ,
for any, yeah.
For any IJ pair. So you have to check it in n squared steps.
Yeah. It's also has to be true for any pair. Yeah. Okay. So strong Schur convexity, like standard convexity, implies strict Schur convexity, but strict Schur convexity does not imply strong Schur convexity. And there's lots of other things we can say, but that's not important. What's important is that this owl norm, so these, as long as these W's are non-increasing, and we have a definition of this norm using this the way we defined it before, then this function is strongly Schur convex with a modulus of strong convexity, which is the minimum of the difference between two consecutive weights. And this is important because this is what underlies the strong preference of this function for values that are exactly equal, that share the same value of some components. Okay, so the L1 norm is not strongly convex, as we saw. It's not even strictly. The L2 norm and the elastic net regularizer are strictly Schur convex, but they are not strongly Schur convex. Okay, and this lemma, as we'll see, will be the key to the proofs. I will not prove the results, but I will show them very briefly. So they all have this kind of flavor. Okay, so if we solve, say, linear regression with the owl norm as a regularizer, okay, then we can show that if the norm between the difference between two columns is less than some quantity, then the corresponding coefficients will be exactly the same. Not approximately the same, but exactly the same. And if they're positively correlated, then the betas will be symmetric of each other. And if we have a standardized design matrix, meaning that the columns are zero mean and unit norm, as is commonly done in data science and machine learning, then we can rewrite these as a condition on the correlation coefficients between pairs of variables. So its correlation coefficient is sufficiently large, then the coefficients, the regression coefficient will be exactly equal. There was a result which is sort of a preliminary version of this in the original paper, but it had a lot of conditions which are not easy to satisfy, and we extended very much. And we extended it to L1 norm. So if you're doing, say, robust regression using the L1 loss instead of the L2 loss, we have a similar result. We can also show it for logistic regression. Again, if two variables are strongly correlated enough, then their corresponding coefficients are equal to each other after you solve the problem. Okay, so this is exact grouping results for the owl norm.
So no, sorry, again.
Yes, go ahead, please. Yeah, no problem.
No result for general convex loss.
It
seems that just I don't know.
It's probably if you you probably need like Lipschitz and strong convexity.
Yes, something like this. So in this class, okay.
Yeah, probably yes. We have not looked at them. So one very important feature of these is that you can achieve this clustering of features without having to compute correlation. So this is a property that you can guarantee, but you never need to compute these rows. You just solve a problem, a regression problem using this norm, and you guarantee that any pair of variables that have correlation above some value will be clustered. They will be together in the sense that will have the same regression coefficients. And you don't need this to spend this P squared cost computing all the correlations. You only need, I will not show you, I won't have time, but the cost of solving these problems is, it scales as P log P in terms of the dimension of P. Of course, it scales linearly with N, but that's no way around. You cannot do better than that. Okay, so we also have some statistical bounds, which I will not have time. Let me see, 3/4. Let me talk for another 5 minutes at most. So to derive the statistical bounds, what we did essentially was to take a design matrix that's correlated, where some columns are correlated, and rewrite it as a product of an IID matrix, an IID design, Gaussian design, with some matrix that imposes the correlations. Okay, and so in a more general sense, this is what happens. Okay, and so essentially we look at these. So this is the covariance matrix of the variables, of the features of the explanatory variables, of the predictors. Okay, and by doing this, we were able to prove a nice but a bit ugly theorem, which I will not try to unpack, but I will just give you two particular cases, okay, which are easy to understand. Okay, in the particular case, which is this one is standard, okay. So in the particular case where C is identity, so you don't have correlated variables. So in the standard case, with nice case where all the variables are independent of each other, our result recovers what is standard, say, from many different areas, from statistics, from compressive sensing, from all these areas, which says that if you have a sparse vector, the number of samples that you need to obtain to keep some level of prediction error, of estimation error, I'm sorry, scales proportionally to S, which is the number of non-zeros, and log P, where P is the dimension of the regression error. So S non-zeros in a vector of size P. And so this log P is very famous. It's got the price you pay for not knowing which S out of P should be non-zero. And this is a result that has been proved in many different ways, in different tools, and we recover it using yet another different tool, but this is for when there are no correlations. So when the covariance matrix is identity, great, simple case. A more interesting case is when you have correlated predictors, but the design matrix is still full rank. So you don't have any pair of features that are perfectly correlated. So you have a full rank design matrix. In this case, we recovered a famous result from Raskuti and other people, which looks like this. So there's a price you pay. So with respect to the classical result here, with the square root of S log P over N, this is penalized by this condition of this design matrix, lambda max over lambda mean. So if lambda mean becomes very small, this quantity becomes very large. And so your upper bound on the estimation error degrades, okay? And furthermore, you cannot use it if lambda mean is 0, okay? If the design matrix is ranked efficient, because you have some set of perfectly aligned predictors, then this explodes to infinity, and it's not important, it's not interesting, okay? So it does not apply in the presence of identical columns. Whereas our result, what it still applies in the case where you have perfectly replicated columns. I will just show you how it looks like. So the estimation error, it still has the same scaling. So S log P over N, everything is the same. What you have to do is reinterpret what you mean by prediction error. So prediction error here in this case, or sorry, estimation error, not prediction error, is with respect, is between your estimate and the version of the true vector, where in the positions where you have the perfectly correlated columns, you put the same copy of the coefficient. Okay, so you recover its, I don't like to go back in slides, but it's exactly this situation. I'm sorry. I know this is awful, really bad to go back in the slides. It's exactly this situation. Still going back. Yeah, oops, it's here. Oh, I shouldn't have done this, I'm sorry. This. So this is beta hat. This is what I'm calling beta star bar. It's this version. Okay, so this is not this is just to make sure that I was not cheating. Okay, so I would not spend any time. So sorry, sorry to Emmanuel, who's an optimizer. I will not spend any time talking about optimization, but this can be solved efficiently in different versions of the optimization problem that you want to solve, either standard way, which is minimize the sum of the loss with the regularizer, or minimize the loss with an upper bound on the regularizer, or vice versa. There are different methods that you can use, and for different choices, you have different things that you need, either the proximal operator or the projection on a ball of this norm to do projected gradients. All of them can be computed. The key thing is that all of them can be computed. I won't have time, of course, to go over this. The key thing is that all of them can be computed with the P log P. So the most expensive operation that you need, and it's not surprising because you have these, you are assuming that things are somehow sorted, is sorting operations, okay? All else is order P, and then of course you have n samples because so everything in the end scales linearly with that. So that's an important issue. So I'm not going over this. So let me just show you the next thing would be talk a little bit about multiple regression, but let me talk a little bit about deep neural networks, just to give like a more modern taste, and then I'll stop. So in deep neural networks, there's a lot of ways, there's a lot of interest in doing parameter sharing. So for example, convolutional neural networks, we know that parameters are shared across in a spatially invariant way. But it's possible that there are other parameter sharing that should be applied. And we applied these to try to learn the parameter sharing directly from data in the context of deep neural networks. So this is just an illustration of what we mean by this. So we mean that, so some coefficients, say these red lines are sharing the same value, these blue lines are sharing the same value. And the way we do this is by using growl, which I didn't have time to explain in detail, is the group version of OWL. So OWL is a norm for a vector. Growl is a norm for a matrix applied to the columns of that matrix or to the rows of that matrix. It doesn't matter. And so what we do is we train a neural network using a standard neural network training algorithm, but using also this growl operation. And from these, we extract cluster information, that is parameters in the network that should be shared, that would share the same value. And then we impose this structure and we train, and we get this parameter shared sparse deep neural network. And we've tried it in different data sets and different network architectures, and it works very well. Essentially, it typically depends on the problem, of course, but it is able to learn some sort of sharing on top of sharing that is already built in the network, such as convolutional structures, and without any loss in accuracy, or essentially very minor losses in accuracy. So this is other people are using this now and trying to, because it's a very important topic in deep neural networks, is sparsifying them, saving parameter counts. And so this is one of the tools that may be useful in that context. So another application is subspace clustering, which I will not address in the interest of time. I'll just wrap up by saying that Oscar is a regularizer that is able to identify groups of correlated variables in supervised learning problems, namely in logistic and linear regression. We generalized it to this OWL norm, which contains Oscar as a particular case. Using that, we were able to prove results, namely concerning exact clustering conditions. So under what conditions do we guarantee that the coefficients will be exactly clustered, exactly tied together? We also were able to prove some statistical complexity bounds, sample bounds. Computationally, we show that it can be handled very efficiently, because everything the most expensive operation that you need to do is sorted. So it's p log p, where p is the number of coefficients. Everything is p log p, and I'll talk a little bit about extensions and applications. And thank you for your attention. Sorry, I went a little bit over time.